Okay, I've got to continue here. Not sure when the class is going to be able to respond and get back, but we'll have the video. So, again, we're trying to fit y equals ax cubed plus bx squared plus cx plus d to 4 points. And in general, we can fit a polynomial of degree n to n plus 1 points, and it'll fit perfectly. And the whole process is just totally analogous to what we did here, except we're going to get a 4 by 4 matrix because we've got 4 points. We'll get one equation for each point. So we're going to get four equations in unknowns A, B, C, and D, and we can proceed. And we can proceed either by inverting the matrix or by a row reduction. Makes no difference. Okay, I've continued. You can hear me, can't you? Hello?
Yes, sir, I can.
Okay. Yeah, good. I'm not sure where we cut off, but I think it was pretty close to right here, where we had 4 points, and there's a third degree polynomial that goes through these 4 points. My modem crashed, and I've got to do something with my provider. I paid them more than the price of a modem for that modem. They need to replace it. This has happened several times. First time I think it's happened in the middle class, though. Always at a bad time, but there are no good times. Okay, so anyhow, we're fitting a fourth degree polynomial with parameters A, B, C, and D to 4 points. Well, we do the same thing we did over here. We're going to get 4 equations and 4 unknowns, A, B, C, and D. And we can proceed. We're going to get a 4 by 4 matrix, an A, B, C, D, and 4 numbers over here. Or we're going to get a 5 by 4 matrix, augmented matrix, that we can reduce and find our solution. So, it's one pretty important application. When you, well actually I was going to say when you go to Excel, it does something like this, but you're actually going to see what Excel does before too long. Okay, so we have that application. Now, with all the aggravation and so forth, got to look back to see. Okay, we can do the same thing to the circle. Okay, if we got these 3 points, we can fit a parabola, but we can give it a little more curvature, and we can make it into a circle. So if we have 3 points, there is a unique circle through any 3 points. And they could actually share their x-coordinates. That wouldn't be a problem at all. This isn't a function. Okay, that is a function, so it's not going to work. But for the circle, you should be familiar with the fact the form of a circle is x minus h squared plus y minus k squared equals r squared. Okay, it's just like x squared plus y squared equals r squared for a circle about the origin, but you just transform it by shifting h units to the right and k units down, and then you get a circle that's centered someplace else. Okay, well that's where the equation comes from, but we can plug into the equation. Well, some issues come up, but they aren't serious, and you can learn through doing your WebAssign problems. It's not difficult. No more difficult than this is. Okay, so there's one more application that's pretty important, and no way I want to try to squeeze that onto that little space on the board. Now you might not be familiar with electrical circuits, and maybe you are. Let's just say we've got an electrical circuit where we've got a resistance here and a source. Now this is much like a circuit that you're going to see on your homework. Okay, so this source has some voltage which we'll call V1. This one has voltage V2. This one has voltage V3. This one's trying to push current from, well, it's actually trying to push negative charge if it's a metal circuit, but we think of it as pushing current from positive to negative, okay? And that means it's pushing current this way. This one's trying to push current this way. This one's trying to push current this way. You have a resistance here and a resistance here. And you've got some rules. Whether you understand the physics or not, the rules are pretty simple. You're going to have a current through this source, and we'll call that current I1. Now, you're never sure, depending on how big these currents are, they might be pushing, they might overpower this one and push the current this way through this thing. It doesn't matter. If they do, and you assume it goes this way, then you're going to get a negative for the current when you solve the problem. Okay, so what we're trying to do is solve for the currents. Okay, so you have a current that goes here. You have a current that goes here. We'll call this I2. And we'll have a current I3 here. And we'll put a big old circle right here because this is called a node. And as a result, you have current I3 flowing into this node, current I1 flowing into this node, and current I3 flowing out of this node. Okay, so at this node we see that I1 and I2 flow in, and I3 flows out. Another thing is that the charge carriers can't accumulate unless you have something equivalent to a capacitor, because they repel each other. Okay, if all your charges accumulate at this, they repel each other, and they can't accumulate because they repel each other so strongly. So whether you understand that or not, the rule is that the sum of all the currents into a node has to be 0. And we could write the same equation over here. Okay, the current I1, now another thing is the current can't change in a series of wires and so forth unless there's a branching point. So whatever current flows here is also flowing here. You have just one current flowing through this, well, from this node down through V1 into this node. So you have that 3 still doesn't look like a 3, so I'm going to really make it into a 3. You have I3 that ends up flowing into this node. You have I2 and I1 that flow out of this node. And current can't accumulate, so all those add up to 0. Okay, you also have voltage drops across a loop. So I'm going to say, okay, we've got a loop here. And we've got a loop here, indicating that we can go around here, and we can go around here without any branching. So this loop has voltage drops. Okay? Let's call this loop 1, call this loop 2. Might not be able to read that, but this is loop 1, this is loop 2. Okay, in loop 1, if you go from here to here, from the short, which is the negative terminal, to the long, which is a positive terminal, your voltage goes up. So if you go from here to here, your voltage goes up by V1. If you go around the loop to here, your voltage goes down by V2. And if you go through a resistor, your voltage goes down by the product of the current and the resistance. Now your book will give you the details, but in loop 1, you really talk about voltage drops. Okay, the voltage drop from here to here is negative V1. The voltage drop here is positive V2. And the voltage drop across here is, well, if the current was going this way, it would be the current times the resistance. The voltage drops in the direction of the current. But the voltage drops in this direction, so the voltage drop as you go around this way is negative. So you say we have a negative voltage drop, I2, R2, okay? And that's the total voltage drop. Well, voltage is a potential function related to potential energy. You have a closed loop, you have a conservative force, and you understand that from a little bit of physics. Since force is conservative, this is really an expression of conservation of energy. Okay, so we have this. Now, this alone with these two gives you 3 equations in I1, I2, and I3. We assume that we're given all the resistances and voltages, so now we can solve for the currents, because we have 1, 2, 3 equations and 3 unknowns. So we have x minus I3 and I negative I1 minus I2 plus I3 equals 0. So we can solve these as simultaneous equations. It's very straightforward. Now, generally, we want to rearrange these. So I'm going to do it I1 plus I2 minus I3 equals 0. Negative I1 minus I2 plus I3 equals 0. And now, surprisingly, I find that if I add this equation to this equation, I get 0. So because of the way these loops interact, this equation tells me exactly what this equation does. Meaning it's worthless. So now I've only got 2 equations and 2 unknowns. So I've got to set up the loop two equation. So I go around loop 2. So in a very real sense, then we say that what happens at this node is not independent of what happens at this node. So there's something very much like linear independence of nodes. And these nodes are not linearly independent. Okay. Again, I'm not going to go into too much detail about that, but what we find is that one of the equations is going to, if we do a row reduction or whatever, it's going to reduce to 0, or this is a multiple of this. If we try to do the inverse matrix, one of the rows is going to be a multiple of the other. The rank of the matrix is going to be less than its dimension, and we're going to be out of luck. Okay, so we set up the equation for loop 2, and that says that if we go around in this direction, we do have a voltage drop here. I3 times R1 is a voltage drop. We have a voltage drop here, but the voltage rises here by V2. Okay, so the equation, and again, you probably have to read your book and look at some examples to totally understand, is I want to line it up with this one. V2 plus I3R1 minus V3 equals 0. And then we write the equation for loop 1, which is going to be minus I2R2 plus V2 and minus V1 equals 0. Now I don't have things real well lined up, but what we're going to do now is we're going to put all our voltages over on the other side because those are known. The unknowns are I1, I2, and I3, so we can write the equation now as I1 plus I2 minus I3 equals 0. And then we're going to have I3 R1, which I'll write as R1 I3 here, and that's going to equal V3 minus V2. And then here we have R2 I2 equals V3 minus V2, and I think I did it wrong. This should have been V2 minus V1, and this should be V3 minus V2. Let's see if I can make that just a little. Yeah, this board is kind of rough, so it's kind of hard to get smudges off of it. Okay. Anyhow, there are three equations in I1, I2, and I3, and we can write this then as a matrix equation. What matrix times I1, I2, I3 equals 0, V2 minus V1, V3 minus V2. Well, the matrix is going to be 1, 1, negative 1. That multiplied by this is going to give us I1 plus I2 minus I3 equals 0. And then R2, so R1, I should be able to read subscripts. And then here, so here's our matrix. It's going to be really easy to either solve this by flipping this row and this row, which gives an upper triangular matrix, and we can just solve by back substitution and all that stuff if we do an augmented matrix. And it's also going to be pretty easy to invert the matrix. Pretty simple matrix. And then multiply this by the inverse matrix. Well, you're not going to become an expert at setting these things up from what I just told you, and after you read the book you'll be a little better at it and do a problem or two. I think there are problems in the set, I don't even remember, but this is an important application. Just to convince you that there's some real applications to this stuff. Now that's just chapter 1. Okay, so now we know how to fit a curve to any given number of points, a polynomial that goes right through all the points. And we know how to solve a network of resistances and currents and voltage sources. Okay. Now we want to go on in section Well, the last section of chapter 3, we have applications of the determinant. We want to talk about some of those applications.